Hello everyone. So today we're going to go over section 4.3, characteristics of polynomial functions. So we'll begin with definition of polynomial functions. A polynomial function of degree n can be written in standard form and will look like this. Now, each of the a values listed here are real numbers, and each of the n minus 1, n minus 2, and so forth, those will all be whole numbers. So an example of a polynomial function would be something that looks like this. So we have f of x is equal to x squared plus 2x plus 1. So in this case, the first a value is 1, the coefficient in front of x squared, then 2, then a constant, which is the a0 term here, would be 1, or a naught would be 1. The coefficient of the highest power, in this case of the x squared, is 1, and that is usually called the leading coefficient. And those are the kind of defining characteristics of a polynomial function that we just looked at here. All right, so let's continue. So this is just an example. So some of the polynomial functions that we'll look at are going to be familiar, and other ones will be a little bit new. The first one we have is just y equals to -4. So that is a constant. And in that case, the degree will be 0. It's a constant, so we'll just write constant here. Now, in order for a leading coefficient to be a leading coefficient, it has to be in front of a power of x. So in this case, y equals -4 does not have a leading coefficient. So it's very important to note that. And the last piece is the constant term. In this case, of course, it is -4. Okay. Next up, we have the highest power of x is 3. So this is degree 3. The type would then be cubic. Leading coefficient in this case, of course, is going to be 3. And the constant term is 7. Next up, we have x squared minus 16. The degree is 2. Then I'm just going to do this vertically. Afterwards, 8x to the 4th power is degree 4. Negative 2x plus 9 is degree 1. And finally, the last polynomial is degree 5. So we have seen before a degree 2 polynomial is quadratic. A degree 4 polynomial is known as quartic. Degree 1 polynomial is linear, as we've seen before. And finally, a degree 5 polynomial is quintic. And of course, the degree of these polynomials continue to increase, so x to the 6th power, 7th power, and so forth. But we're just going to cover these 6 different types. And the leading coefficients, of course, are 1 in front of the x squared, 8, -2, and finally, -1. And then we have the constant term of -16, 0, because there's no constant term, 9, and then -7. So the reason why we are always going to be looking at the type of polynomial and the leading coefficient and the constant term is because it informs us as to what the shape of the graph of these polynomials will be. Okay. So, of course, there are are functions that are not polynomial. So for example, 4 to the power of x, that is not a polynomial. It does not fit the description in the box above. So this is not a polynomial. And the second function, we can rewrite it as negative 4x cubed plus 6. And of course, that is a polynomial. Okay. So a few characteristics of graphs of polynomial functions before we look at the graphs themselves on page 2. Smooth and continuous graphs, so no sharp corners. So for example, an absolute value function is not a polynomial function because it has a sharp corner. And it can be drawn without lifting the pencil from the paper. A point where the graph goes from increasing to decreasing is called a local maximum. So if the graph ever moving from left to right does something like this, that is a local maximum. Likewise, if it goes from decreasing to increasing, then this point here and this point here are local maximum and local minimum respectively. And the end behavior is the behavior when of the y values of the function as it says here absolute x becomes large. So either the x value is becoming very negatively large or very positively large. What happens? Okay. So instead of just looking at this, we can look at some graphs on page 2. So important to note is that these are specific polynomial function of each type, and of course there are other possibilities, but it just gives us an idea of what they can look like. First thing, however, is to recall that the quadrants goes 1, 2, 3, and 4. Alternatively, we can also write this as Q1 for quarter 1, Q2, Q3, and Q4. Either one is acceptable. So usually when we're talking about end behavior, we talk about where the graph is coming from quadrant-wise and where is it going to end. So in the case of y equals negative 3, a constant function, degree 0, and degree is even, 0 is even. Its end behavior is going to come from quadrant 3 and end in quadrant 4. So for end behavior, simply write Q3 to Q4. Okay, next up, maximum minimum point. Well, the constant is negative 3, so the maximum slash minimum value is just negative 3. Okay. Number of x-intercepts. Now, this particular constant function has no x-intercepts. However, it is entirely possible to have something like y equals 0, then it will have many x-intercepts, right? So, what else do we have here? Just going to go ahead and delete this. Oops, let's not do that. There we go, that's better. All right, so moving right along, we have y-intercept. Y-intercept is going to be negative 3, right? That's where it crosses the y-axis. And finally, the range of this graph is just a single value, negative 3. All right, next up we have a linear function. Sorry about moving the screen back and forth there. So it's going to be y equals to x plus 2. So in this case, it's going this way. We can see the y-intercept is 2. The slope is 1. So the end behavior is coming from quadrant 3, and it's going to end in quadrant 1. And that is the case for positive linear function. If they're negative, they will come from quadrant 2 to quadrant 4, like so. Maximum minimum point, it doesn't have one, right? It's just a straight line, so it doesn't have a maximum minimum point anywhere. Number of x-intercept, it has exactly 1. It is at -2. But we're just interested in the number of x-intercept that it has. The actual y-intercept is 2. And the range of this function is y is an element of the real numbers. So right, so notice that the domain for all these polynomial function will be x is an element of the real numbers. It's always going to be that for polynomial function. There are basically all x values are you can substitute it into polynomial and it'll give you a y value. So there's no restrictions in the domain. All right, next up we have a upside down parabola. So y equals to negative x squared plus 4. So the y-intercept is 4. And the range is y is less than or equal to -4. There are 2 x-intercepts. It has a maximum point at 0, 4. And also, its end behavior is going to be from quadrant 3 to 4. Kind of did everything backwards. All right, so far, we have looked at 2 polynomials of even degree. So that would be the constant and the quadratic functions. And then we have one odd polynomial function, so degree 1. Notice that the end behavior for the first and third graphs are both quadrant 3 and 4. So the idea here is that, like, let's see, we have y equals 1 for our graph. It will go from quadrant 2 to 1. So the idea is if we have an even polynomial function, its end behavior is going across, so it's either 3 to 4 or 2 to 1, depending if the graph is positive or negative. Whereas if the polynomial function is odd in degree, then it goes diagonally across the plane. So it's going to be either quadrant 3 to quadrant. This is not quadrant 3 to quadrant 4. This is quadrant 3 to quadrant 1. Sorry about that. Uh-oh. I just deleted a bunch of stuff. Right, so let's erase this. Gonna fix that. 1. This is so this is a good time to remember to save once in a while when we're working. So this is quadrant 3 to 4. The maximum point at 0, 4. 2 x-intercepts. Y-intercept is 4. And it has y is less than or equal to 4 as the range. Okay, that's better. So going back to what we're saying about the odd function, it will go diagonally across. So either 3 to 1 or 2 to 4 will be the end behavior. So the idea is one of them will go horizontally across and the other one will go diagonally across. Next up is the max and min point. So the idea is if a function is even, then it will have maximum minimum values. Whereas if it's odd, then it only has local maximum minimum values. We'll look at that in just a second. Also notice that the y-intercept is always just a constant term in all 3 cases. -3 for the first one, 2 for the second one, and 4 for the third. And finally, even polynomial functions have limited range, whereas odd polynomial function have a range of y as an element of the real numbers. Okay, let's continue on. Next, we have a cubic function. Again, it is negative, so in this case, it's coming from quadrant 2 to, and then in quadrant 4. So let's write that down. Notice that it doesn't have absolute maximum or absolute minimum. It has a local minimum here. So the the points that are next to it has greater y values, and then on the right we have a local maximum, and that is to say the y values next to it or in its neighborhood are all smaller. So it doesn't have absolute maximum minimum point, so that's none. It has one x-intercept. A cubic function can have at most 3 x-intercept, as we'll look at later. The y-intercept is 5. Once again, it is the constant term, and the range y is an element of the real numbers. As we can see here, the graph will continue to travel upwards on the left and down towards negative infinity on the right. All right, so next one is the quartic function. Can continue on here, and behavior then is going to be from 2 to 1. Notice that this is a positive graph. Now it has a minimum point. It's hard to tell what it is, but it's approximately negative 1.6 and then negative 4.2. So the minimum point is approximately at that location. Right, number of x-intercepts has 4. So a quartic function is degree 4, and it can have up to 4 x-intercepts. It can have 0, 1, 2, 3, or 4 x-intercepts, in fact, depending on the actual function. The y-intercept is 2, and then the range, we can see here, y is greater than or equal to negative 4.2, again, approximately. Finally, we have one more to look at, the quintic function. Again, it is negative because the leading coefficient is negative 7. So it's going to come from quadrant 2 and then in quadrant 4. For a odd polynomial function, if it's negative, it's going to come from quadrant 2 and end in quadrant 4. If it is positive, then it will come from quadrant 3 and end in quadrant 1, as we saw on the linear example. Whereas even polynomial function, if they're positive, will be from quadrant 2 to quadrant 1, and then if they're negative, will be from quadrant 3 to quadrant 4. Okay, so it doesn't have any absolute maximum minimums. It only has one x-intercept. In this case, it could have up to 5. The y-intercept is negative 3, and a very familiar range at the end. Okay, so the question that we might have is how can we graph these if we don't want to necessarily use a table of values, because that's probably the easiest way. And we'll look at that in the next lesson. For now, what we want to look at is how we can determine the characteristics of a polynomial function with just the function just the equation and no graph. Okay, so let's look at example 4a. It is quintic and it's positive, right? So those are the characteristics that we note immediately. So if it is quintic, means degree 5, and it's positive, it's going to come from quadrant 3 and end in quadrant 1 as its end behavior. Okay, and then it asks possible number of x-intercepts, so it's up to the degree. So it's up to 5. And it has at least 1, because the range has to be y as an element of the real numbers. So it has to cross the x-axis at least once. And it also asks for the value of the y-intercept. It's going to be +2. Okay, next up, the second example here for b, this is a cubic function. Notice that the middle term is negative 7x cubed. So it's going to be negative. So one way the question can be tricky is for the terms to not be listed in order. So in this case, since it's negative, it's going to be coming from quadrant 2 and ending in quadrant 4. Cubic function, again, is odd, so this is going to have up to 3 x-intercepts and then at least 1. Again, the exact number of x-intercepts cannot really be determined without graphing the function. The y-intercept is -6. Again, that's just a constant term. And this is why when we were filling out the table before, we are looking at the type of polynomial, so its degree, and whether its late leading coefficient is positive or negative, because that tells us a lot about its end behavior, number of x-intercept it has, and then the y-intercept. All right, a couple more. So the next one is quartic, degree 4, and it is positive. So it's going to come from quadrant 2 and end in quadrant 1. Oops, that's not the best one. There we go. Now, this graph, since it's even, it has up to, and degree 4, it has up to 4 x-intercept, and it can have 0 x-intercept. The entirety of the graph can be above the x-axis. And then the y-intercept is just -1. All right. Finally, the last example here. Okay, this is a simple quadratic. You might have graphed this before already. Oh, sorry, can't spell quadratic. That's not how you spell quadratic. Quadratic. That's better. And again, it is positive, since the x squared is positive. So this will be from quadrant 2 to quadrant 1, up to 2 x-intercept, so 0, 1, or 2, and a y-intercept of, once again, -1. Okay. So that's how we can determine some characteristics of polynomial functions without graphing them. Okay, finally, last part here says sketch a polynomial function with the given characteristics. So again, it has to be smooth and continuous curves that we're graphing. So let's see here. Polynomial function of degree 3. Okay. Positive leading coefficient. So that means it's going to come from quadrant 3 and end in quadrant 1, and 2 x-intercepts. All right. So let's make one of the x-intercepts negative and the other one positive. And so it's going to come from quadrant 3. Oops. Something that looks like maybe that. It's going to have to cross the x-axis. It's going to have to come back down. But it cannot go too far down. It cannot go below the x-axis again, because that will make, let's say, for example, if it did this instead, that will be 3 x-intercepts all of a sudden. So it has to change direction right at the second x-intercept and then go upwards. So this is only just one way of drawing a possible graph. Of course, there are other possibilities. For example, this right here, that was called double root, can occur on the left-hand side instead of the right. It doesn't specify if it has to be one or the other. Okay, so there are certain. So for this type of question, there are certain solutions are correct, but there are some variations as to what can actually be drawn. Second one, polynomial function degree 4, negative leading coefficient, and 4 x-intercepts. So we can just draw the x-intercepts anywhere, maybe like this. So there are 4 of them, and the graph is going to come from quadrant 3 again and end in quadrant 4 because it has a negative leading coefficient. So it's going to do something like this, come back up, cross over again, something along the lines of that. This middle part was not the best, but that's a bit better. Polynomial function of degree 5, negative leading coefficient, and 3 x-intercepts. All right, so what does that look like? So let's do 1, 2, 3 x-intercept, negative leading coefficient, so it's going to come from quadrant 2 and end in quadrant 4. So maybe something like this. So let's see, 1. So I have to change direction here. And then something like this. So the fact that it's degree 5 means that it has to have a couple of what's called double roots. We'll examine that further later on in this unit. So there's a double root here. It just touches the x-axis and changes direction. And then it has a double root here. And every double root counts as basically 2 degrees. So this will be 2 plus 2 plus 1 for a total of degree 5. And finally, it says here, even polynomial function with no x-intercepts and a range of 6. The only way to really draw that is to draw a straight line, horizontal line at y equals 6. Since the only polynomial function that has that kind of range is the constant polynomial. Okay, so that is an introduction to the characteristics of polynomial functions. This will be examined further in later on in the unit, but that's it for today, so thank you for listening.